Alright, so I'm recording now. This is hello, my name is Ashton. This is week 2. I guess the second week of me doing the statics weekly review. Last week we went over chapter 2, and I kind of just wrote some stuff here just to kind of familiarize yourself with what we did over chapter 2, right? So we learned like law of sines, law of cosines, directional angles, how to write forces and their components, add them up, how to write force in terms of a position vector, a dot product, all that good stuff. We talked about that last week. So just put that up here just to kind of give you a refresh of that. So this previous week, chapter 3, is all over free body diagram. So I'm going to be doing the same thing as last week. I'm just picking out some random problems in the book, and I'm just going to work through them from chapter 3 to see what chapter 3 is trying to teach us. All right, so I'm going to go ahead and clear this. And I'm going to start off with, let's start off with problem 3. And problem 3, let's do 3.3, 3-3. All right. Again, I'm using the statics and mechanics book. So I'm going to try to draw out the picture of the question here. Basically, it's want us to determine the magnitude and direction of a force so that the particle is in equilibrium. So got this here, and there's a particle in the center. Like that, there's a force this way of 5 kilonewtons. There's then call this theta. There's this. We call this 4. And this right here. 8, 30, 16. Okay, so here's the question. So they want us to find the direction and magnitude, so this direction theta, and this force, so that the particle's in equilibrium. All right. So I guess chapter 3 was all about free body diagrams, right? So we're going to draw a free body diagram for each one of these forces, which will look kind of like those arrows there. So my free body diagram, I'm drawing right on top in blue. It's going to look like that. And I'm going to draw it like this instead. Something like that would be our free body diagram. And we want to break each one of these vectors into components on the x or the y, on both actually, so that we get some equations so that we can solve for that force there. All right, so let's get started with that. So start by writing the sum of the forces in the x direction, all right, have to be equal to 0. Or overall, this is the condition we have, right? All right, that's the condition of equilibrium. Sum of the forces have to be equal to 0. And since that's a vector, this equation kind of breaks into 2 more equations, one for the x and one for the y. So sum of the forces in the y have to be equal to 0. All right, we've seen that before. So adding up the forces in the y, starting with this one over here, the y direction would be cosine, or actually sine, the opposite side over there, right? So, well, actually I'm gonna start with the x, with this top one. So let's start with 5. Yeah. So this one's 5, it's gonna be equal to 0. I've got 5, that one 5 here in the x direction. We have this force here that we're trying to solve for in the positive x direction. So I write plus f sine theta, right? Because the x component of this force is the sine component. And there's these other two forces in the x direction that are both negative. So, all right, negative 8 cosine 30 is that minus 4 cosine 60. Cosine 60. All right, so this is an equation we have for the x direction, and we get one more from the y direction. And basically the idea is we're going to combine those equations and we can solve for that force. So for the y direction, starting with that 8 kilonewton force over there, it's going to be 8 sine 30, right? And minus, it's that 4 sine, what's that, 60, and it's pointing downwards, so they're minus, and there's one more, right? Minus f, that's cosine theta. Okay, so let me rewrite both of those equations now. Let's see what they say. So if I take this one, I'm gonna take this equation in the x direction. I'm just gonna solve for f sine theta. I'm gonna solve for this here. So f sine theta equals, we'll add over. So plus 8 minus 5. Okay, so now we've got this equation here. Let's do the same thing for the y direction, but I'm gonna solve for, let's solve for the force cosine. So doing that, just add that over. That's actually pretty easy. F cosine theta equals, so like this is just algebra. Let's see, that's supposed to be a sine, right? Sine is 16. Okay, so it looks like we can basically solve for both of those, right? So combining these two equations, we can actually solve for the angle. If I can divide these two equations, right? Divide these two. So that the f's here and cancel out once I divide these two equations. And then get something like, it's a different color. Let's see, sine theta over cosine theta, right? And so that equals tangent theta. Okay, going down here, right? Basically dividing these two equations. So let's see. I guess we could have put that in. Cosine 30 is what, square root of 3 over 2. Cosine 60. Sorry, I wrote it, so let's do this. This is a half minus 4 square root of 3 over 2. Right. Okay, so we put that into our calculator, then we can solve for the angle theta. Yeah, so once we do that, let's see. We should get something, theta is equal to, negative 2.2. Okay, so now that we have this theta, that actually solves for this angle theta that they were asking for. Okay, and we can use that to solve for the magnitude. So we just take this and plug it in here. right? Especially if we take like f sine theta, we know what all this is. That's just the number we plug into our calculator. So I plug in 82 degrees with that. So f is going to be equal to, well, once you do all the math, you should get 3.96 kilonewtons. Check my work. Yeah, that looks right. Okay. So again, that came from this, where I just plugged in the angle and divided it over, and I was able to solve for f. Okay, not bad, right? Not bad. So basically, the whole idea was, we've got all these forces here, we break them into components, x and y, set it equal to 0, use those two equations to kind of solve for whatever we need to solve for. So let's do another example. Hopefully I'm not going too fast, but it's recorded so you can kind of go back and look at it. I'm just trying to get like a good amount of examples in, because the more you see, the more you understand, I guess. So the next example I'm going to do, let's do 37. I like how that one looks. And let me draw the picture for it. It basically says, draw a picture first. Alright, so this is the picture. The question says, the man attempts to pull down the tree. I guess he's trying to pull down this tree here. And the man attempts to pull down the tree using the cable and a small pulley. Okay, so this is a small pulley right here. If the tension in AB and AB, they're calling AB the computer here. So we'll label that. Right there, AB. The tension in the rope right there, AB, is 60 pounds. Determine the tension in the cable CAD and the angle theta, which makes the cable a pulley, where this here is theta. They're calling this point here C, this point here D. And they tell us that these two parallel lines here, this one right here, this parallel line here, that is 20, right here it's 30. Okay, so that's the picture. This guy here is pulling on this rope. So let's draw the free body diagram, and then I'll repeat that question. So this guy here is pulling on this rope. Tension here. Let's just call it tension T. And there's two more on either side of the rope. I guess we could call it one like this, one like that. I guess we call this one tension C. Call the other one tension D. All right. So now, let me redraw that so it looks like a little better. So, because this is our free body diagram, so we want to break those forces into components and kind of analyze what's going on there. So let's see. Actually, no, I think if you look at this, I guess we got to ask ourselves, how do we want to make our coordinate system? Do you want it like that? Yeah. think it'd actually be easier. Excuse me. Okay, so yeah, we want this to be our coordinate system right here in the blue, or we can, I think it'd be easier to write it like this. I have to redraw that picture so I can kind of show you. Let's make it big here. Just want to make this kind of clear because I think it's hard to see with that little picture. Just want to get my point across. All right, so something like this. Okay. And I guess what I'm trying to say is, do we want our coordinate system to be up and down and like perpendicular with this dotted line? Or I think a better way to do it would be if we made it perpendicular with this force here. And I guess I'll also say this, the tension in both of these ropes is going to be the same. So since the pulling, this is the thing with pulleys. If I have something like this, something like this, and say TC equals TD. So basically the tension on this side of the rope is the same as the tension on this side of the rope. So these two we can just call T. So let's just set equal to T. Let's go ahead and call this tension T, T, and the tension in this rope over here is 60. This right here is the 20. This is 30. So I'm gonna draw both of the reference frames. You can do it like this. You can use that. Let's say coordinate system, or we can make another one, which I guess you wouldn't initially think of this, but I kind of want to show it because it's a good trick to have in mind. And my picture's not that good, so this is one of the two. It looks something like this. Something like that. It's another kind of where it's basically parallel with this rope here that's at 20 degrees. So it's above this one. Where we can say like since this is 30 right here, right up here, this is 30. So this right here is 30. You can kind of see that. Okay, so why am I bringing that up though? So let's look at it. I guess, kind of look at that. Let's call that other coordinate system y prime and x prime. And let's write out the equations for the coordinate system in the red, the x and y, and I can do the same thing for the y prime and x prime, just to make a point here. So I'll do x and y. So we've got the sum of the forces in the x So looking at that, there's this rope here. It has a positive x at this angle of 30. So let's write this 60 cosine 30 minus t cosine 20 minus t cosine 20 plus theta. T cosine 20 plus theta. Okay. So where did that come from? How did I get that? So that came from this rope right here, right? Because we have to project it all the way down to the x axis here. And so it's basically 20 plus it's theta plus 20. So 20 plus theta, that's how I got that there. Okay, so I guess you can see how that might be some trouble, which is why I mentioned this other coordinate system here, y prime and x prime. So let's go analyze that one now, because we see that might get tricky. So I guess you could work it out with some trig identity, but I'm not sure how clean that would be. So let's do the sum of the forces in the x direction for x prime, where that's this coordinate system here, x prime. So there's a small angle right here, right? That's projecting this tension in the rope that the guy is pulling. There's a small angle right there that projects onto the x prime axis. Let's look at that. Zoom in on that right here. That angle right there. So if we're projecting, this force onto that x, we have to use that small x prime. We have to use that small angle. So can we figure out what that is? Well, I think we can. We know from here to here is 20. So here to here must be 20. Alright? So from kind of draw that in. So you can see that from here to here is 20. So from the dotted line right here to the orange is 20. Right? If my picture were better, it would make more sense. This line should be like more, the dotted line, yellow dotted line should be more straight, but I think you can kind of see what I mean. And then, so this whole thing's 30, this little piece is 20. You should be able to subtract it to get that little red angle. So this little red angle should be 30 minus 20. 10. So it's real small, makes sense. So the x component of this 60-pound force is going to be cosine of 10. So onto x prime. 60 cosine 10. Okay, not bad. Minus t minus t cosine theta. Okay, so notice how that worked out. So it's just this t by itself minus t cosine theta, because this t is along the x axis, x prime axis. So, we don't have to break it into components, but we do have to break this other one into its x component. But it looks a lot cleaner than, the first. Okay. So let's keep going in. So the question was, what was the question? Determine the tension. So we're trying to find t. Okay. Alright, so now let's do the y prime direction. So the sum of the forces in the y prime direction, all this equals 0, right? Y prime direction, we got, it's gonna be 60. Oh, that should be minus 60 sine 10. It should be a minus, right? It's a minus in there. Because it's below, right, the x prime axis. So that's the negative y direction. Okay, and then one of these t's is in a positive direction, so plus t sine theta. Okay, so let's see what that does for us. So let's take this first one, simplify it by, I guess let's just solve for the t, right? So it becomes t, combine like term, parentheses, 1 plus cosine theta, set that to the other side, equals 60 cosine of 10, right? I just combine like terms right there and move on to the other side. Key. Let's see, what else can we do? What does the second equation tell us? Is that gives us, I guess we can say t sine theta equals 60 sine 10. Ah, that's interesting. 10. Okay. What can we do here? I guess we could try to divide what that is, what that is. Let's see, if we're dividing, this might be tricky. Well, I know one thing we can do, we can rewrite this. Let's see, take this part. So we can rewrite that, that's a trig identity. I know that one off the top of my head. That one's 1 plus cosine theta equals 2 cosine squared theta over 2. Theta over 2. Okay. What can we do with this sign? If we'll just divide both of those, turn it to tangent. No, would have had, yeah, no, still would have been a mess. Yeah, the t's would have canceled out anyway. I guess what I should do is use this one, solve for t, and plug into the other. And see if that works. So what I'm saying is like, take t, say t equals, all right, you can plug that into the top one. Oh, actually, I think I see a better way. Put this. So, yeah, I hope all that makes sense up to this point, though, right? basically wrote this new coordinate system x and y prime so that we can get these two equations to solve for t. It still might be just as tricky as using another way, but I think I see a path. So I'm gonna start back off with these two things. Flip off with this. Okay. Those two last equations I had. It's kind of what we got from setting the forces equal to 0. Is that sine or cosine? I think it was supposed to be cosine. And the other one. Positive 60, 10, 10. There we go. Okay, so that's kind of what I'm thinking. What I have in my notes here. This is going to become t cosine theta over 2. That little thing is squared. And this going to become, let's see, t out like that. Okay. Okay, so that's a trig identity I pulled, and let me see if I can pull that up for you, that one. Okay, well, yeah, so that's a trig identity. I think you can look that up. And now we can divide these two, because now if you kind of look at it, if we divide them, got a sine over here, a cosine over here, and it looks like some of these sine and cosine and stuff would cancel out. So let's do that. So let's go kind of along here. Let's see t, sine. I want the sine on top. I want the sine on top, so I can set that equal to tangent 10. And let's see down here, 2 cosine squared theta over 2. Okay, and looks like that simplifies a lot. I think that goes with that, that goes with that, that goes with that. This with that. One of these cosines with this whole thing. Yeah, okay. So notice how this sine over 10, cosine over 10 gave us tangent 10. So this is going to give us tangent theta over 2. Okay. Guess that helps us solve for theta. So we can say theta equals 2 arctangent of tangent 10. Interesting. Okay. So once we do all that, we get theta is equal to 10, 20. Okay. So I guess that helps us out. So now we can just take this theta, which I guess we're supposed to solve for that anyway, and plug it in to either one of these equations. So plug it in right here, or right here. This is actually a shorter one. Plug in theta there, and we can solve for t. Right. So 60 sine 10 or sine 20, where this was basically theta. You know, theta is 20 now, so solving for t should be about 30.5 pounds, 30.5. Okay, so that one was a little bit more tricky, just because of how we have to go about solving it. We have to do some more like trig rules and rewrite some things a little differently. And so you may not have thought of that initially, but it kind of works out pretty clean in the end. I'm sure there's other ways you could have did it, but I don't know if they would have been as smooth. Okay, so let's do another one. That was problem 37. 37. Let's jump up. Uh, guess let's do this one. Let's do 13. Guess one more. Let's not jump to a spring one. So I'm gonna do one with this spring. So that was the one with the pulling. So kind of what we have to know about the pulley is how the forces are the same on either side. So now I'm gonna do 13. This is kind of another pulley problem, similar to the first one, or the one we just did. It looks like this. Okay, so that's our pulling. There's this force here. It says this block has a weight of 20 pounds. This block here has a weight of 20 pounds. 20 pounds. And it's being hoisted up at a uniform velocity. So if the velocity is uniform, except the acceleration is zero, so the system's in equilibrium. Okay, determine the angle theta, which is this here, for equilibrium and the force in the chord AB. This is A, C, and they're calling this D. So if I draw the free body diagram, it's gonna look something like, draw it right here. That's this and this. So that's my free body diagram there. And let the other stuff in. This is theta. And oh yeah, they also tell us this here. They tell us this. This here is 20. So that's basically saying, like if I draw a little line here, it's saying this is 20. Right? So I can say this here is 20. Okay, and let's label each one of those. So let's call this is labeled the way they have it. Let's call this tension E. This force here is 20. Wait, no, that's not that force. This force here is 20, right? That's the weight. guess let's call it TAC. Okay, so TAC we know is 20 because that's the weight of the box. This box right here. And I guess I should also say real quick, like this box here, this box right here, right, has its own free body diagram. Alright, that looks like this right here is tension. Oh my god, I've been muted. I hope I wasn't muted long. I think my arm was on it. Okay, so yeah, I don't know where I left off at, but I was saying, um, I guess I was talking about how this tension, the free body diagram for this box right here is shown by this little picture, and how the weight and tension CA basically balance out. So that's why this weight is the same as the tension in this row, TAC. And then I was saying how since this is a pulley, and tension on this side of the pulley is the same as the force on this side of the pulley. So this force then is going to be 20. And then I was saying, yeah, we can do the sum of the forces now. So sum of the forces in X is going to be, well, actually, it's going to be 20 sine theta minus TAB sine 20 equals 0, right? So yeah, and let's go ahead and let's rewrite that solve for TAB. So we see TAB is going to be equal to, let's see, add that over and divide 20 sine theta. Okay, so now let's do some of the forces in the y direction. Let's see what that does for us. So I'll write it right here. Y direction, that's going to be TAB positive. This is going upwards. Cosine 20. Let's see. There's two forces going downwards. That's minus 20 minus F cosine 20. Wait, yeah, no, that's 20. They're both 20, right? So 20 cosine 20. 20 cosine 20. Yeah. Okay, all that equals 0. Let's see. Let's solve for TAB again. All that equals 0. So actually, let me just take this. I'm gonna take this, plug it in down there. Right? Basically, plug it into the other equation so I can solve for theta. Let's see what happens. So we got 20 sine theta over sine 20, excuse me. Cosine 20 on the outside. And let's just set that equal to 20 plus 20 cosine 20. Okay, so we can combine that cosine over sine. Combine this cosine over sine right here. It's going to be 1 over tangent. So let's see. Then we're basically going to have it's like sine and that sine theta is going to be equal to tangent 20 times 20 plus 20 cosine 20 all divided by 220. Guess one of those 20s. No, that's tangent 20, so this just cancel. I guess cancel that. With those two. Well, okay, so using that, now plug all that into a calculator. Yeah, put that in my calculator. Just checking my work here. Make sure I did that right. And combine those two. Tangent. Let's pull that over. Okay. Yeah, and then do the arcsine to get the angle. Okay, so the angle is going to be 40. Okay. So now I can take that angle and plug it in where to solve for tension AB. I guess I can plug it in right here. Right here, right? So TAB. Twenty sine 40 over sine of 20. Okay, that gives us tension. All right, so I think that gets the point across as far as how these pulleys work. They basically have the same force, so it's always good to notice that when you have pulleys. Now let's do one with the spring. Those are good too. 21. So 321 looks like this. Try to speed this up. It's like a yeah. So it's this situation here going on, and to determine the unstretched length of spring AC, so we're calling this middle point A, And yeah, so determine the unstretched length of spring AC if that force is pulling down here is equal to 8 pounds. So go ahead and write that in. So the force being pulled down here equals 80 pounds. And what else? So that's that. There's tension over here to the left. It's called tension AB. All right. I guess we don't have to because it's on. Let's call that. Let's just call it T because we know this over here is going to be force over spring. So let's call that Fs spring. Where we know force on a spring is equal to the stiffness K times S. And let me finish the question actually. So to determine the unstretched length of the spring AC, if a force of 80 pounds causes an angle of 60 degrees for equilibrium. So over here, that's 60. That's a bad 6. Yeah, okay. So 6 degrees over there. And the chord AB is 2 feet long. Okay, and they also tell us this length. Interesting. That's 2 feet. Okay, so this thing here is in equilibrium. These two forces are in equilibrium. You can also think of it as basically these two forces, the tension force and the spring force over here, balance out to A. And so you can also treat this as a triangle here. Treat this as a triangle. And you can imagine, well, yeah, you can imagine this vector that's force pulling downwards would be kind of associated with this long end. And they also have this in the picture too for us. That from here to here is more. Okay, so that gives a good amount of information because if you look at that, it kind of looks like it's supposed to look like that, where this is 4, this is 2, and this is 60. Okay, so that should look like it's doing something there that looks familiar. And we're trying to find an unstretched length where basically S here, S is equal to L minus L naught, where L is the unstretched original length and L is the length in equilibrium, you could say. So right now, while it's in equilibrium, this thing has a length of L. So it's here, over here, this is basically L. Key. So that looks like one of those times where we can use the law of cosines to solve for this side, right? Because we know the angle opposite of that side, and we know either the other sides of that angle. So law of cosines, that doesn't give us the answer. That just gives us L. That just gives us L, but that's good to know. So I think it's what L square root of 4 squared. plus 2 squared minus 2 times 2 times 4 times cosine of 60, which is basically a half. Let's see, 4 times 4, 16, 16 plus 4, 20, 20 minus 2 times 4 times 4, 16 divided by 2, 8, 20 minus 8, okay, 12. So L equals square root of 12. Okay, that's good to know. What else would be good to know from that triangle? Well, let's bring this free body diagram over here and point out a few things. So, right, that's our free body diagram. You know this right here is 60 because that's this side over here. So, you know, if that's 60, then here must be 60. But we don't know anything about the angle of this force. So it would be nice to know at least what this angle is, or this angle. Nice to know what that angle is. This angle up in here. This is called psi. And that would basically give you this angle, right? Okay, so that'll give you that angle. And so from the point of view of like looking at this one, be able to decompose these forces, it makes sense why I would want that angle, right? Because it lets me decompose this force. Okay, so from here, and the fact that we know this L, I think it's pretty straightforward. Oh, and we actually have to solve for psi, right? Well, we can solve for psi. Let's see. So using the law of sines, right? We can say 2 sine psi equal to, well, there's any of the other sides. Let's do I guess L. So L goes with 60 times 60, or L squared root of 12. So in the algebra, we rewrite that to solve for sine. Sine 60 over the square root of 12. Square root of 12. So putting that in, you should get 30. Okay, so no, that's 30. So this should be 30. Okay, now we can go ahead and get the sum of the forces. So sum of the forces in X, spring force, cosine 30, which is square root of 3 over 2, minus tension T, cosine 60 equals 0. And so now we're looking at that spring force. So spring force is going to be equal to cosine 60 over cosine 30. All right, using the sum of the forces in the y direction, I'm trying to speed up so I can do one last question after this. So y direction at the spring force. Sine of 30. Zero. Okay, so I guess you can basically see how we can solve for t. Then I guess use this one down here and solve for t and plug it in up here, or vice versa actually. Solve for t here and plug it in down here to solve for the spring force, but I'll leave that to you. That's just, algebra and whatnot. But you should get the spring force be equal to the equal to 40. So I'm skipping to this, so spring force equal to 40. Or another spring force is equal to Ks. Okay, so K is going to be L minus L naught. Well, we know K, we're trying to solve for L, not the unstretched length. So, and we know L from here. So plugging all that in, doing algebra divided by K, subtracting over L, we get L to be L not to be 2.6 feet. Okay. Unstretched length. Alright, so not bad. What was the trick there? I guess the trick to what the idea was is spring force, and how the spring force is equal to L minus L, K, S, and S is L minus L naught. Cool. And just kind of remind you, sometimes you still might have to use these law of sines and cosines. Okay, so let's do one more these last few minutes. So let me jump up a bit. Let's jump up to like a three-dimensional one. Up till now, we've just been in 2 dimensions, so let's show the 51. 3D1 dash 51. Okay, so I'm gonna just jump right into the picture. So there's this force upwards here. And there's a point that goes over here. Call that point B. There's a point over here. Yeah, there's a point. So right there. Something like that. Okay. So basically, to determine the greatest force that can be applied to the ring if each cable can support a maximum force of 800 pounds. So each one of these cables can only support 800 pounds. And we're trying to find the greatest force this F can be so that none of those cables break. And so each one of those points. That's over here, C. It's gonna be a little hard to draw. But if you have the picture, I wish I could just pull it up and write on it. I guess next time I'll do that. Flip the slides and I won't just write on them. Alright, so I'm doing 51. I have to write this way bigger. So I've got this length right here. Got this length right here. So that's that. There's another one right there, there. So now if I label all of these, this distance right here is 2. This distance right here is 30. This distance here is 2. This one right here is 3. Okay. This distance right here is 1. This distance here is 3. Okay. So that's the picture we got there. Hope that makes it more clear. X, Y, Z. Call this point B. Call this point B. Call this point C. Okay, so the free body diagram, well, this is in 3 dimensions, so I guess it's like a 3-dimensional free body diagram, right? But you can imagine it's right here. I guess I'll draw it in red. Looks like this. So let's label this force over here force B. Let's call this one force D. And let's call this one underneath here force C. And so, of course, this is an equilibrium, so we have this same condition here. Let's start off with that. And so now we're going to have 3 equations because it's in 3 dimensions now. So let's start with this. Let's start with the Z. Yeah, let's start with the Z. I think that looks the easiest to me. So sum of the forces in the Z direction equals 0 equals, well, we got that force F upwards that we're trying to solve for minus. And let's see, all the other forces are going to be minus because they're all pointing downwards on the z-axis, right? So automatically know that. Let's start with force B. So force B, let's see. Tell us how high things are. They do tell us how high. Okay, that's what I'm missing. They also tell us how high this is. That's 6. Okay, that's gonna help. Yeah, so I think that helps because now we can kind of make a triangle here for the I guess it's force B actually. B kind of pointing right there. We can make this triangle where it's kind of like this, right? That triangle, and we know this side is 6, and if we're analyzing that triangle, we're using this angle. Let's see, this angle right here. And we want the z component of that force. So looking at this triangle, it would be cosine of 6 over whatever hypotenuse of is here. So I guess we have to know what this side here is. Kind of see how I drew that. This side here is basically going to be another triangle. If we find the hypotenuse of that triangle, it'll be this bottom red triangle. This bottom red triangle, right? So the hypotenuse of that angle is the side of the purple angle. Or better yet, I think it'd just be easier to write like position vectors, right, for each one of those. And then, with position vectors, we can actually do this, right? I think I'm doing it the hard way. We can do this. You had. Okay, I think that'd actually be easier. So let's find each point here. This is point A. Point A is 0, 0, 0, 0, comma 6. Point B, so the point B. Point D right here is -2, comma, it's supposed to be a Y. -2, comma, that goes up. 3, comma, 0. C over there. Back there, it's going to be, what's that, -3? -3, comma, let's see, -1 in the Y, comma, 0. Okay, then B, 3, 3, comma, -2, comma, 0. Okay, so now that I got each one of those, I have to make a unit vector that points this way. So it goes from A to B. From A to B. Okay, there we go. So RAB, I guess I'll just do one of them to kind of get the idea. So RAB is going to be, well, the final position minus the initial position, right? So final position is B. So it would be equal to 3, comma, -2, comma, 0, minus 0, 0, 6. So 3, comma, -2, comma, 6. Okay. -6, right? So now we can find the magnitude. Well, we can say the magnitude of AB. So RAB, magnitude, square root of 3 squared, comma 2 squared, plus 7, plus 6 squared, square root all that. That gives you the magnitude. So then we can take this. We can say force is B is equal to magnitude of force B times U AB. Okay, so then we basically repeat that process. Once we do that, that will basically give us all 3 components, the X, Y, and Z component of force B. And then we can do the same thing for the other 2. So we'd have to do that same thing for force, that's force B, force C, force D. Right, so repeat that process here where you find a position vector, final minus initial. So, A minus D, A minus C, so on and so on. Find the magnitude of it, then you'll have the unit vector to apply to each one of those forces to make them Cartesian vectors. Then you can set this condition, summon them, and then set them equal to 0. And let me clear the screen to kind of show you at least what I get when I do all that. I get this for the sum of the forces in the x, sum of the forces in the y, sum of the forces in the z. We'll start there. Got the force F minus force B 6/7 minus force C 6/46 minus FD 6/7. All that equal to 0 for force Y. Let's see, I get force D 3/7 minus force B 2/7 minus force C 1/46 equals 0. For the x direction, force B 3/7 minus force C over 46 minus force D 2/7. 0. Okay, so you see now we've got these three equations, three unknowns. But what we want to do is we want to figure out what the greatest force is, right? So I guess we have to look at each one of these tensions, force A, B, and C. Which when we do that, we get this. Force B. Force D. All right, so we get these values when we kind of solve for the equations here, when we solve for each one. The force C is 0.2 of F, force B is 0.5 of F, force D is basically 0.4 of F. So, looks like this one here, force B, has the greatest tension, right? Because it's multiplied by the biggest number. So we want to set that one. Now we want to set F equal to 800 for that one, because F is the greatest force. And if this one has the greatest tension, then automatically, if we solve for FB, these are like going to be less. So let's see what happens. Well, we'll set FB equal to 800. Set FB equal to 800 because it has the greatest tension. So then we can solve for F. Okay, and then say F is going to be equal to 1,558 pounds. Okay, so that's kind of all I have time for, but yeah, so you can see how kind of leveled up from doing it in 2 dimensions to how it'd be in 3 dimensions, and how we had to basically use unit vectors so that we can create these forces and turn them into Cartesian vectors, right? By using unit vectors and getting these 3 equations. combining those three equations, kind of looking at them, and we're setting the one with the greatest tension. Well, we set the one, yeah, this one has the greatest tension because it has the biggest number with F. So we set that one equal to 800. So that automatically, if we apply this force here to force C, it's going to be less than 800. If we apply it here, it's going to be less than 800. Okay. What's it say about that? No. Yeah, so that's it for this week. I hope those were some good examples. I'll be doing this again next week. Hopefully I get better and better as far as with the examples, maybe the pace of which I'm going in, and all that. So yeah, see you next week.